Hey friends, we're in chapter 6 and we're looking at section 6.6 and we're going to talk about something that's going to seem off topic, but then it'll be back on topic. We're going to talk about organizing information or data using matrices. And matrices are just an array of numbers, so you're just like writing numbers in lines and columns, and you might have an internal understanding of what those lines and columns means. It'll make perfect sense. Here we go. We have a couple of vocabulary words to talk about. Nothing too deep. The first one is this concept of matrix. A matrix is, let me get my pen here, a matrix is a rectangular arrangement of numbers in rows and columns enclosed in brackets. So basically you would see something of this effect when we talk about it: 2, 4, 3, 7, -9, 2, 1, 5, something like that. And the orientation of it can be different depending on what you need it for. And so when we talk about a matrix, we're talking about an organization of numbers, but each number is considered an element. So an element is a single number in a specific row and column of the matrix. So like right here, 3 happens to be in the first row but second column. 2 happens to be in the second row and third column. So each one of those guys, each one of those numbers is considered an element of the matrix. The dimensions, when we talk about the dimensions of the matrix, we're literally talking about the number of rows and the number of columns. And the number of rows always goes first and the number of columns always goes second. So in this case, we would talk about this particular matrix as a 2 by 4 because there are 2 rows, 1, 2, and 4 columns, 1, 2, 3, 4, right? A scalar is a constant that is used to multiply the elements of a matrix. And when we talk about a scalar, really it's just a number that might hang out on the outside of your matrix. So let me change my matrix up a little bit. 2, -1, 5, and 0. So now I've made a 2 row by 2 column matrix, right? And a scalar would be 4. And basically it's just a number on the outside of the matrix that means you're going to multiply through. So in a way we're using, and I don't think we'd use this word, but we use kind of a distributive property. 4 would have to be multiplied with each element within the matrix. So the resulting matrix here that I'd have if I multiply it with 4 is going to be 4 times 2, which is 8. 4 times -1, which is -4, 4 times 5, 20, and 4 times 0 is 0. And scalar multiplication is just what you saw me do. It's the act of multiplying with a scalar. So now that we have those terms in place and kind of the concept of a matrix in place, let's go ahead and take a look at some matrix or matrices. Matrices is actually the plural of matrix. So we're going to take a look at some matrices and some examples. Let's take a look at the first one. So the first example is simply asking us to practice the concept of figuring out what the dimensions are for a particular matrix. So as I look at this matrix, remember, we do rows by columns. Okay, rows by columns. And when we do rows by columns, we see that here we've got 1 row and 2 columns. So this is a 1 by 2 matrix. What about this one over here? How many rows do we have? 1, 2. So it's a 2 by how many columns? 1, 2, 3, 4, 5. 2 by 5 matrix. What about the dimensions here? Here we have 1, 2, 3 rows and we have 2 columns. So this is a, sorry about that, this is a 3 by 2 matrix. Pretty simple, right? Not too hard. So we'll get into a little bit more work when we start thinking about how we use matrices or how we can use a matrix. So here we have a certain movie theater. The matinee will cost $5.25 for an adult ticket and $4.50 for a child's ticket. When we have and the evening admission is $8.75 for an adult and $5.75 for a child. The question is basically asking us not to do much, but just to organize this information in a matrix. And what are the dimensions of the resultant matrix? When you think about organizing things in terms of a matrix, in a way, you're thinking about making a table, right? So we'd have adult and maybe child, and that would be our columns, and then our rows would represent, let's say, the matinee price and then the evening price. And once we've decided what we want where, and this is not strict, you could have had the adult and child here and matinee and evening here, we're going to fill in this chart that I'm creating with some numbers. So what is the adult matinee price? Well, we realize that that's $5.25 from our example, from the information given. The child matinee price is $4.50 per ticket. The evening price for an adult is $8.75. And then the child price is $5.75 if you're purchasing that ticket in the evening. So what we end up having, I'm going to get a better pen, is $5.25, $4.50, $8.75, and $5.75. And what these actually do is they create an organized rectangular array of numbers, which is our matrix, right? So this matrix represents the situation, and look how we took it right from the actual table. So what I will do is finish the question, organize the prices into a matrix, did it, and what are the dimensions of the following matrix? 2 rows and 2 columns, so we get a 2 by 2, or a square matrix because it's the same both dimensions. Got it. All right, let's go ahead and look at the next example. Here in example 3, we're going to add matrices together. And you can only add matrices together or subtract. This is like a rule. So this is pretty important. You can only add or subtract matrices when they have exactly the same dimensions, okay? So some of the problems here we won't be able to do. So here we've got that. Let's name this first one A. A is given as this matrix, B is given as this matrix, and C is given as this matrix. We're asked to add A plus B together. If you notice, A and B both have the same dimensions. And so what I'm going to do, let me do this in red and scroll down a bit. What I'm going to do is literally just add element to element as they're in exactly the same place. So 12 plus a -4 would give me a +8. I didn't use another color, did I? Will give me a +8. 2 plus 4 gives me a 6. -9 plus a -3 gives me a -12. And 15 plus -10 gives me 5. So this is the answer to the sum of those two matrices. All right, not too bad, hopefully not. So if I were to, now I'm going to be a little bit lazy and not rewrite B. If I were to take B and grab it over here, so I'm going to add to B C, right? Or maybe I should copy that. Let me try that again. So copy it so I don't ruin the same thing. Guys, I'm learning. Thank you for your patience. So if I copy, boom, and then paste, bam. Aha, there it is. So I got 2. So I'm going to leave this one over here. All the time I took to do that, I probably could have just rewritten it and it would have been fine, but you know how technology. All right, anyway, so I'm going to now add to that the C matrix, which is this here. And already, I told you before that they have to have exactly the same dimensions. These don't. So there is no answer here that I can get. And there's my other color. There's nothing I can do. So there's no way to add that. So I'm kind of done. Let's go ahead and take a look at this example here. So here I have a couple of other, couple of matrices here, A, B, and C, which two have the same dimensions. Hopefully you guys see that A and C have the same dimensions, so we can't really operate with B. Remember, addition and subtraction require that you have exactly the same dimensions. So A minus C is going to work out, but B minus A, this matrix minus this matrix will not work. The subtraction here won't work. So I'm just going to not even bother drawing it. I'm going to put a line there. And then what we saw happen with addition is going to happen with subtraction. We are simply going to subtract each element from the other element. So in the proper place, right? So 4 minus 1 is going to give me 3. -2 minus a -3 will actually give me a +1. 8 minus 5 will give me 3. -17 minus a -10 leaves me with -7. 10 minus 8 gives me 2. And 6 minus 7 leaves me with -1. And so what we see here is that when we add or subtract a matrix, or 8 matrices from each other, we end up with the same exact dimensions of the following or the resultant matrix. Let's look at this final example. This final example actually brings us full circle to what we talked about earlier when we defined scalars and scalar multiplication with matrices. Basically, it says if matrix A is as follows, we've got this thing here, what would 4A be? So 4A would be 4 times the matrix as you see it there, right? And so if I'm simply multiplying, I said that this is going to really harken back to, it's not called this, but it's going to really look like distributive property. I'm going to multiply 4 by each term in the parentheses. And notice when we do scalar multiplication, the dimension will also remain the same. 4 times 2 is 8. 4 times that gives me a negative 16, negative 28, a positive 36 here, a positive 4, negative 40, positive 32, and finally a positive 24. So this is the resultant matrix that we got after scalar multiplication. And it's kind of easy, right? Not too bad. We're going to actually use this later and apply it to solving systems of linear equations. So we just need to really get the practice and the handle of working with adding, subtracting, and multiplying with a scalar. So that's why we're doing this at this point in time in the chapter. And the other thing is matrices get much deeper and even more interesting that we've seen here. You can actually multiply matrices themselves, but they have to have a specific dimensional relationship. And that's something that we'll talk about at a later time, or if you guys have any questions and you want to discuss it, I'd be happy to. I look forward to seeing you guys soon. Let me know if you have any questions, and take care.